Let's say that we have two sets. A contains the elements 1, 2, 3, and 4. And B contains the elements 3, 4, 5, 6, and 7. Now, we might want to produce the union of this, right? A union with B. And we might also want to know how many elements will be in the union of this. So that's the cardinality, right? Where we use the vertical bars. Now you might be tempted to do this, say, well, if we're unioning these, it's the count of A plus the count of B. But what happens when we do that? Well, A has 4 elements. B, we can see, has 5 elements. So the sum here is 9. But remember, when we find the union, we eliminate redundant elements. So the union of this is not 1, 2, 3, 4, 3, 4, 5, 6, 7. It's actually 1, 2, 3, 4, 5, 6, 7. So the union has 7 elements. So what we have to do is actually subtract back out the duplicate elements, which are in the intersection. Because in this case, what we have is this situation. 1, 2, 3, 4, 3, 4, 5, 6, 7. Right, so we have 1, 2, 3, 4, 5, 6, 7. We're 3 and 4 in the middle. So we get our 4 plus our 5 minus 2 is equal to 7. So this part right here is the intersection of A and B, and that's where the redundancy comes in. This idea of adding the cardinalities and then subtracting out the additional elements, the extra elements, is called the principle of inclusion and exclusion. All right. So where might we use something like that? Well, let's say that we have 40 people and we ask them, I'll say people, what kind of desserts do you like? And we give them the choice of ice cream and pie. And they should indicate all that they like. So what if we have 35 people say they like ice cream and 23 people say they like pie? And the question is, how many like both? So using this formula here, we can say, okay, there were 40 people total plus the 35 that like ice cream plus the 23 that like pie, or 40, excuse me, is equal to 35 plus 23 minus B. So B equals both in this case. And so what do we get? This would be 40 minus this right here is 58, which is equal to minus B. So we have minus 18 equals minus B. And we get that B is equal to 18. So 18 of the people are in the intersection. They like both of these. Now what if we want to find the union of more sets? This particular problem is not that bad. But when you start thinking about having more and more possibilities, then it becomes more painful. And before we leave this, let's talk about what I had drawn before. So I drew this picture, but these aren't the only possibilities. We also could have had, they're completely separate things. We could have had that A was inside B, it's a subset of it, or we could have had B was a subset of A. So does our formula still work in these other three scenarios? Well, what would we have here? Well, here we have that A union B is just the sum of the two, right? Because this would be A plus B minus what? Well, minus the empty set. So we don't subtract anything. So this is the only time when, if there's 15 things here and 10 things here, we just add the two together to get 25. What about something like one of these two scenarios? So let's look at this one. Well, what do we have here? Well, it turns out in this case that B is actually the same as the intersection of A and B. So when we have the union of A and B is equal to A plus, or the cardinality of A plus cardinality of B minus the intersection, these two are the same. So really the union of the two is just however many elements were in A to begin with. So the formula does work. Now, what if we want to extend it? So let's write, I'm going to do this. So remember that when we think of our properties of sets, we have the associative property. So this right here is equal to the union of A with the set that results from the union of B and C. So this is a set. We could think of this as D. And so if we go back and use our rule, this becomes the cardinality of A plus the cardinality of B union with C, whatever that set is, minus the intersection of A with the union of B and C. And now this becomes A again, plus, well, the union of B and C is just our formula. So that's B plus cardinality of C minus cardinality of the intersection minus, we have a distributive property here. But I can probably just fit that here. Minus, this is A intersected with B unioned with A intersected with C. That's the distributive property of set theory. Okay. Which is equal to, we have A plus B plus C minus B intersected with C minus, and we have, use our property again, this right here, minus, and it'd be, I'm going to use parentheses to push the minus sign through here in a moment, but this would be, if this is like the original A, right, the left thing, this would be the cardinality of A intersected with B plus the cardinality of A intersected with C minus the union, or excuse me, the intersection of the two. And so this would actually be this, A union, or intersected with B, intersected with A intersected with C, so we can do some simplifying. So here I still have A plus B plus C minus B intersected with C. And now we'll take the minus through. I actually have three things here, this, this, and this. But what is this right here? Well, the intersection of A with B intersected with A and C is really just A and B and C all intersected together. So this right here really just reduces to A intersected with B intersected with C. And so I have this, so minus this, minus this, and then minus minus, so this becomes plus. That right there. So normally you would see it written this way probably, where they'd be in order, some kind of order. A plus B plus C minus A intersected with B minus A intersected with C minus B intersected with C plus A intersected with B intersected with C. Okay? So let's use that for solving a problem. So let's say now that what we have is 50 people are surveyed. For movies they like. And the options are action, comedy, and dramas. All right. So we find out that 15 like action, 23 like comedy, 21 like drama, 10 like action and comedy, 12 like action and drama, and finally 19 like comedy and drama. Right? So one of these things I didn't list was, what about people that like all three? So what we have is this scenario: action, comedy, drama, and we want to know how many people are in this part here, the intersection of all three, which in our formula is this last thing. Okay, so A by itself is 15, C by itself is 23, D by itself is 21, and then this part where A and C overlap is the 10, where A and D overlap is the 12, and where C and D overlap is the 19. So 50 is our total. And so that's equal to 15 plus 23 plus 21 minus the three pairwise intersections, 10 minus 12 minus 19, plus where all three intersect. Okay, so we'll call that X. So this right here, if you work this all out, we end up with X is 32 people. So it's actually rather large compared to the others. Okay, and just like before, this is one way of drawing it. There'd be other possibilities. You could have something like this where you had, say here's A, here's C, and here's D. But we couldn't have that here because this says each two pairs overlap, which forces some overlap here. For something like this, you would have A and D have no interlap, right? There's no intersection between them. You can't have each of these three be non-zero and have this type of scenario. Okay? So that's the principle of inclusion and exclusion. Let's look at one more thing that's relatively easy to understand, but sometimes you still need somebody to point it out to you. And it's something called the Pigeonhole Principle. Give me a pigeonhole. And so basically it says if we have K bins and more than K items, then at least one bin holds more than one item. And the story goes that where the name came from is that you would have these places for pigeons to fit into, and say if you had 20 pigeons but you only had 15 pigeonholes, then some of the pigeons are doubling up. So you might have this type of situation. Let's say some people go to a park and nobody is dropped off. Everybody who comes stays. So let's say you have 4 cars out in the lot, but there are 6 people at the meeting. Well, that means at least one of the cars had to have more than one person, right? Because we have a car, a car, a car, a car. We don't know which one holds more than one or which ones. It's possible because what we have a person here, person here, person here, person here. That's 4 cars, but now we have 2 more people. So we might have something like this, 3 people came together, or it might be 2 and 2 and 1 and 1. We don't know that. We can't tell from all this information. But what we do know is there's no empty slots in a sense. Okay? Or I take it back. There could be, in terms of using the pigeonhole principle, you can have empty slots, but you can't have something not doubled up. So like in computer science, one of the data structures we have is called a hash table. And basically things hash to be in certain slots in the table. All right? Now, you can have overflow, but it could be something like this. You don't necessarily know where things are going. And I'm greatly simplifying in terms of how things are really stored. But let's say we have these 1, 2, 3, 4 slots. Well, you might have that A hashes to here and B hashes to here and C hashes to here. But what if we have D? D doesn't have to go here. Maybe it goes here. But if we have an E, it also has to be at least in one of these slots. So notice there was no way. There's certainly possible to have empty slots. There's no guarantee they all hash out and even out like in this scenario. But there's no way to not have some doubling up of values. In fact, you might have had even something like this. Okay, so we can't have empty slots, but what we cannot have had is something like this, A, B, C, and then say, well, we got 2 more things, and there's no doubling. There has to be some doubling here because we have too many things to fit into the number of slots we have. And that's basically what the pigeonhole principle tells you. So there's 2 additional ways to do counting to add to the multiplication principle and the addition principle that I talked about in my last video.